Hi guys, welcome back to my YouTube channel. So today we will be talking about radiative mode of heat transfer, basically radiation. But before we move on, if you are just stumbling on this channel, please kindly hit the subscribe button. And if you've subscribed, thank you so much for subscribing. Don't forget to like, share to your departmental group, and leave a comment. So let's get right into what we are doing. So radiative mode of heat transfer, basically radiation. It is the heat transfer by electromagnetic waves. It uses the Stefan-Boltzmann Law, which states that radiation energy from a black body is proportional to the force of its absolute temperature at the surface of the radiator. Now, the mathematical expression of this is this. Q equals to this Stefan-Boltzmann constant, the area and the absolute temperature to the power of 4. Now, for actual bodies, our Q is the emissivity times the Stefman's constant times area into brackets temperature of the surface or of the body to the power of 4 minus temperature of the surroundings to the power of 4. So this is the Stefman's constant, which is 5.67 times 10 raised to the power minus 8 watts per meter cube per Kelvin raised to the power 4. So our A rather is the radiating surface area. Our Ts is the surface temperature of the body, or the temperature of the body. Then the T infinity is the surrounding temperature, and this is the emissivity. Now, for a black body, the emissivity of a black body is 1, and it's because black body absorbs all the heat energy that is given into the body. But for gray body, they do not absorb all the radiant energy that is coming to the body. So the emissivity of black body is 1, but the emissivity of gray body is varies. So this is basically the formula that I'll be using for the radiative mode of heat transfer, just to know that. And take note of the constant 5.67 times 10 to the power minus 8. Now, so let's move to the first calculation question on this. A large opaque body with a temperature of 800 Kelvin. Sorry, I forgot to mention. For radiation, the temperature is always in Kelvin. It's not allowed to be in degrees. So, a large opaque body with a temperature of 800 Kelvin is radiating heat. The body is surrounded by a black body enclosure. Okay, that is, the emissivity is 1, and a temperature of 300 Kelvin. At a temperature of 300 Kelvin, the surface area of the body is 2 meters square. Calculate the net radiation heat transfer rate from the body to the enclosure using the Stefan-Boltzmann law. So, what were we given? We write about parameters. So, a large opaque body, so the temperature of the body, which is the Ts, is the 800 Kelvin, is radiating heat. The body is surrounded by a black body enclosure, except the emissivity is 1, at a temperature of 300 degrees. So that means the temperature of the surroundings 300 Kelvin. Now, surface area is 2 meters square. So we have to calculate Q using Stefan-Boltzmann's law. We're not given the constant, but we already know that our constant is, okay, so this is what we are looking for. Our constant is 5.67 times 10 to the power minus 8 watts per meter cube. So we now, to calculate our Q is emissivity times the constant times area, then T s raised to the power 4 minus T raised to the power 4. So do we have all the values? Yes. So we can just input our parameters to get our Q. So our emissivity is 1 times 5.67 times 10 to the power minus 8. What's the area? 2. Then Temperature of the surface of the body, rather, 800 raised to power 4 minus 300 raised to power 4. And what's our answer? So our answer is 45530.1, which is 4.55 times 10 raised to power, this is 1, 2, 3, 4, raised to power 4 watts. And that is our final answer. So just just input your parameters and get your Q. So let's move to the next question. A gray body with an emissivity of 0.75 is radiating heat. The temperature of the body is 600 Kelvin and it is exposed to an environment with temperature of 300 Kelvin. The body has a surface area of 1.5 meters square. Calculate the net radiation heat transfer rate from body to the surrounding. So we're given our emissivity to be equal to 0.75. The temperature of the body, which is 3S, is 600 Kelvin. Temperature of the environment is 300 Kelvin. The area is 1.5 meter square. Now this one is a gray body. That's why our emissivity is not up to 1 compared to the first question that it's a black body. So we have to calculate our Q. We're not given the Stefman's law constant, but we know it to be 5.67 per minus 8 watts per meter cube. So this is equal to Q is equal to area then C is raised to power 4 minus 2 raised to power 4. So our Q now is 0.75. 5.67 times 10 to the minus 8. What's the area? 1.5. Then 600 raised to power 4 minus 300 raised to power 4. So what's this going to give us? So our answer is 7.75 times 10 raised to power 19 watts. So that is our answer. Let's move to the third question. A small object with an emissivity of 0.85 is radiating heat at a rate of 500 watts. The object has a surface area of 0.2 meters square and is surrounded by a large enclosure at 300 Kelvin, which can be treated as a black body. Assume the objects behave as a gray body. Determine the temperature of the object. So now we're giving our emissivity to be 0.85 and the rate, which is our Q, to be 500 watts. The surface area to be 0.2 meters square and is surrounded by a large enclosure. So that's our temperature of the surroundings. That's this. So you ask to determine the temperature of the object. Okay, we're given this to be 300 Kelvin. Now let's calculate Ts. That's the surface temperature or the temperature of the body or of the object. So our constant law 5.6 cost times 10 power minus 8 watts per meter Kelvin per. So now we have Q equals emissivity times this and Ts minus T surroundings. So we're giving our Q to be 500. We're giving our emissivity to be 0.8. The constant is 5.67 times 10 power minus 8. Our area is what? 0.2. Then Ts is what we are looking for. And we're giving our T surrounding to be 300. So this is 500 equals to, let's multiply all of this together. So all of this is 9.639 times 10 power minus 9 and Ts minus 300. Let's divide through by this. So just divide by 9.639 times 10 power minus 9. Let's divide by, so this is going to cancel this. So 500 like this. We have 5.187 times 10 power 10 equals to Cs minus 300. So 5.187 times 10 power. Sorry, I didn't include raised power 4, raised power 4, raised power 4, raised power 4, raised power 4. So this would be plus 300 raised power 4 equals to Cs raised power 4. So I'm going to add this together. So addition of this is giving us 5.997 times 10 power 10 plus 2 Cs. So to get our Cs to be 4th root of 5.997 times 10 power 10. So this is 494.87 Kelvin. So approximately 495 Kelvin. So the temperature of the object is 495 Kelvin. So let's come back in. So we're giving our emissivity, the rate of the radiative heat, the area, the temperature of the surroundings, and we know our Stefman's constant, and we have to calculate the Ts, and we know all of this. This is what we are looking for. We know the rest of it. So all we did is input our values. We got this. So let's move to our next question. A cylindrical pipe with an outer diameter of 0.3 meter and a length 2 meter is maintained at the surface temperature at 100 Kelvin, 1000 Kelvin rather. The pipe is exposed to an ambient surroundings at 200 Kelvin and the surface emissivity of the pipe is 0.85. Calculate the net radiative transfer. So let's write out our parameters as usual. So we're giving diameter to be 0.3 meter. We're giving our length to be 2 meter. Then we're giving the surface temperature to be 1000 Kelvin. the ambient temperature to be 200 Kelvin and the emissivity is 0.85 and our constant is 5.67 times 10 to the minus 8 watts per meter. So we have to calculate Q, and our Q is emissivity times constant times area, then T s raised to power 4 minus T raised to power 4. So do you have our emissivity? Yes. Our constant? Yes. The area we're not giving, but we can calculate it since the cylindrical pipe. And our area is 2 pi RL. So that's 2 times 3.142. What's R? We're not giving R, but we're giving diameter. So that's divided by 2, 0.15, and the length is 2. So we have 1.8852 meter square. So we can now calculate our Q. Emissivity is 0.8. Constant is 5.67 times 10 to the minus 8. Area is 1.8852. Then TS, what's TS? 1000 raised to power 4 minus 200 raised to power 4. So what's this going to give us? So this is 90711.84 watts. And that is our answer. So let's move to the last question on radiative mode of heat transfer. It says a gray body with an emissivity of 0.8 is heated to 427 degrees C. The surrounding temperature has a temperature of 127 degrees C. The body has a surface area, should be surface area of 0.5 meters square. Calculate the radiation heat flux emitted from the surface of the gray body. So we're giving our emissivity 0.85. The body temperature, that's TS, 427. But since it is in degrees, you have to convert to Kelvin. So this should be 700 Kelvin. Then we have our surrounding 127 degrees C plus 273. This should be 400 Kelvin. We have our area of 0.5 meter square. So we have to calculate the heat flux. So that means what we have to calculate is Q over E. So let's calculate our Q. Our constant is what? 5.67 times 10 to the minus 8. So Q is emissivity, constant, area, and T is raised to power 4 minus T raised to power 4. So emissivity is 0.85. Constant is 5.67 times 10 to the minus 8. Area is 0.5 and multiplied by 700 raised to power 4 minus 400 raised to power 4. This is going to give you. So this is 5168.91 watts. Now Calculate our heat flux. That's Q over A. That's 5.68.9. What's the area? 0.5. So this should be equal to 337.83 watts per square. And that is that on radiative mode of heat transfer. Do not forget to like, subscribe, share to all your departmental groups. And if you have any question, do not hesitate to drop in the comment section. I'll be right there to give answers to all your questions. Till next time, see you guys later.